So good morning to everyone. Myself Dr.B. Ravi Chandra. I am the Associate Professor of EC Department in EC Department. Today I am here to discuss about the main important subject which plays a vital role in the electronics and communication domain. So today here I am here to discuss about the signal processing, where in this lecture I am going to discuss about the main topic, which is nothing but signals. Following that signals, I will discuss about the classification of the signals and what are the elementary of the discrete time signals and so on. So coming to the syllabus, the contents what I am going to discuss here is nothing but, first I am going to discuss about the introduction to DSP, digital signal processing, later followed by principle and operations of the DSP, then signal, what is meant by signal, then followed by the classification of signals, representation of the discrete time signals, then elementary discrete time signals and classification of discrete time signals. So these are the main topics which I am going to cover in this particular lecture. So coming to the first thing, what is digital signal processing? Here you can see here the name itself is telling digital signal processing. The digital is nothing but the data which consists of all binary digits, that is zeros and one. If you see here, it is related to the discrete values. That means it is values are typically represented in the form of zeros and ones. That means the analog form will be converted into digital form, where that digital form will be represented in the form of zeros and ones. Then after, what is signal? Signal is nothing but a function that conveys the information, often in the form of time varying or spatially varying data. That means these data which consists in that particular signal is nothing but the signal. Then after a combination of both this data and signal, digital and signal, it should be processed, which is nothing but the processing. What happens here means the act of manipulating, analyzing or modifying the data to achieve a desired output. So the combination of these two will be manipulated or analyzed or modified in this processing operation. So overall, what is meant by digital signal processing means it is the manipulation and analysis of discrete time signal using mathematical and computational with the help of some systems like hardwares, computers or specialized processor. So overall, digital signal processing is the two combination of all the digital related data and the information which is present in the signal, and these two will be processed in the processing with the help of some computers as well as the specialized processors. Now next, coming to this, what is the basic block diagram of the communication system? The basic block diagram of the communication we can see here. Starting with the analog input signal, it is given into the A to D converter. Then after that, some conversion will be taken place here, where these analog, the signal will be in the form of analog. It will be in the form of analog signal. Then what happens, it is given to the A to D converter, where the combination of sampling as well as quantization, by the combination of these two, what happens here means these analog signals will be converted into discretized form like this. That means, as we discussed in the previous slide, it will be converted into zeros and ones. So the combination of this sampling and quantization will convert these analog signals into digital form, where we are going to get the digital input signal. Now here comes the digital signal processor. So whatever the encoding done at the transmitter side, at that scenario there will be some addition of noise. So that noise will affect the output at the receiver side. So for that purpose, there will have some different types of computers or some specialized processors which is used to digitalize or which is used to remove all that unwanted signals which is present in the input signal. So after this processing, then it is given to the D to A converter, where this will be the reverse process of the A to D converter. That means the digital form to analog form, and finally we are going to get the analog what we have given at the input side. The original signal will be reconstructed. Actually, this is the main scenario of the communication system, where this is the heart of the communication system, which we are going to discuss in the present upcoming classes. Now next, coming to the next, so what is the need for this digital communication system? So why this digital signal processing is needed for this particular? So for that, you can see need for digital signal processing. Same, actually we have told that the analog signal is given, where after conversion from analog to digital form, it will be distorted. you can see the difference of the diagram. This is the main input signal, where it is after conversion from analog to digital, there will be the addition of some distortion. Some noise is added here, where you can see the difference between the signal at the input side and output side. Then what happens here, the signal processing will be taken place, where to restore all that distortions and to remove all that distortion by applying some different types of processes, and then finally we are going to get the original signal what we have given at the transmitter side. So this is the thing, analog to digital converter, where you can see we are giving the analog signal as a microphone, then it is given to the analog to digital converter, then the processors, some different types of systems which is used to do the processing, signal processing, and again that signal will be given to the DAC, which is nothing but digital to analog converter, and finally it is given to the output for the speaker. This is the symbolic representation of analog to digital converter. So this is the overall introduction related to the digital signal processing. Now coming to this, what is the signal? The main topic, which is nothing but what is the signal? Signal is nothing but, you can see here, the main thing you need to keep it in mind, it is nothing but the measurable physical quantity or impulse such as voltage, current and magnitude. That means the signal which should be measurable, that will be like voltage or current or magnitude used to transmit messages or information. That means one signal what we are sending, it consists of some information, that means that information should be measurable. So now we are in the form of electronics, that's why this measurable physical quantity will be in the form of voltage, current and some magnetic options. Then coming to this is the signal. So we can see here on the y-axis we can represent it with amplitude, and on x-axis it will be represented with time. So by the known of this amplitude and time, this can be measurable. This can be measurable. That's why we are calling it as a signal. So sine wave, a simple example for this signal is nothing but sine wave. So what are the characteristics? As usual, I told you that signals are physical quantities, signals are measurable, signals are analog, and signals contains information. Mostly present, every input signal what we are giving will be analog only. Present days we are sending the digital signals also, but maximum analog signals are given as an input to the systems. So these are the characteristics, and coming to that, as I told you, what is nothing but mean by measurable physical quantity. That means that particular signal should be a measurable. So we can measure temperature, we can measure pressure, we can measure mass, speed, acceleration, torque, voltage, current and power. These all will be in the form of signal where we can measurable that particular information. So to measure this particular information, what is the device? The device is nothing but the sensor device, which is very important, which is used to convert the physical quantities into electrical signals. Why? Because we are in the class where analog signals are electrical. That means these particular temperatures or these particular examples of the signals should be converted into the electrical signals. Though sensors is the main devices which we are going to use in all the particular systems. So overall, the signals is nothing but it's a measurable physical quantity which it can use to transmit the message or information from source to destination. Now, keeping it into mind, classification of signals. The signals are classified into two types. There are analog signal processing and digital signal processing. If you see the representation, graphical representation of this particular analog signal processing and digital signal processing, you can see the sine wave which is representing as a analog signal. It is in the form of analog signal. After conversion, this will be in the form of digital signal. You can see here ones and zeros. It is in the form of pulse representation. So these are the main two classifications of signals. So according to these classifications, these signals are being represented in the form of discrete time signals. So how these signals are going to represent? So there are four ways to represent these signals. The first thing is graphical representation. The second thing is functional representation. Third one is tabular representation, and fourth one is sequence representation. That means whatever we have seen in the previous slide, how we are going to represent, in how many ways we can going to represent means maximum in the four ways we can represent that signals into discrete time signals into this representation. So coming to the graphical representation, how it will be. So you can see one example where it will be given in the form of a signal. Signal is nothing but x of n is one of the signal which is considered, and where the n values For example, x of minus 2 is equal to minus 3, x of minus 1 is equal to 2, x of 0 is equal to 0, x of 1 is equal to 3, so on. So the question will be in the form of, the representation will be in the form of like this. Then this thing will be shown in the graphical form. How means, you can see here. So what is x of minus 2? So if you see here, x of minus 2 is equal to x of minus 2 is equal to, the value is given as minus 3. And similarly, x of minus 1 is equal to 2, x of 0 is equal to, x of 1 minus 1 is equal to 0, and x of 1 is equal to 3, x of 2 is equal to 1. Like this, whatever the data given in the theoretical form will be represented in the graphical form. This is the first one. Now coming to the second one, functional representation, how it will be represented. If you see here, the signal amplitude is written against the value of n. That means the value, amplitude value will be right against the value of n. The signal can be represented using the function representation as follows. How that representation will be in the form of, see here. So this is x of n. This x of n, the value of n will be represented here, minus 2, which is the amplitude. And what will be the value? That is minus 3. That is, x of minus 2 is equal to, the value will be minus 3. X of minus 1 is equal to, the value will be 2. X of 0 is equal to, the value will be 3. Like this, it will be represented in the form of functional representation. This is one way how we are going to represent the signal. The third one is tabular representation. As the name itself telling, the sampling instant, the values n and the magnitude of the signals at the sampling instance are represented in the tabular form as shown below. Now we can see here, the values is given on the column, that is n is equal to 2, 1, 0, 1, 2, and the x of n value is given as 3. That means if x of n is equal to 3, the value will be 2. If x of n is equal to 2, the value will be 1. Like this, this is the third way how we are going to represent the signals in the tabular form. And finally, the fourth one, which is sequence representation. That means it will be in the form of sequence. A finite duration sequence can be represented as follows, like this. X of n is equal to, it is given in the flower bracket with all the values in the sequence. And you can see here one representation which is nothing but arrow mark. That means it shows that the origin value starts from here. So the origin value will start from here. If this arrow mark is not given, then we need to consider the starting value will be 0. This will be the origin. That means if the arrow mark is given, then we will consider the origin starts from that value. If this arrow mark is not indicated, if any sequence, if the sequence is not indicated with the arrow mark, then we need to confirm that the starting value is the origin of that particular sequence. So this is the sequence representation. And the same thing what he is telling, the arrow mark denotes the n is equal to 0. That is x of n. That is n value is equal to 0. So this is the value where the origin is going to start. The first term correspond to n is equal to 0 when no arrow is indicated. What I have told you now, just when no arrow is indicating, then the first corresponding n is equal to 0 I am considering. Fine. So a finite duration sequence that satisfies the condition x of n is equal to 0 for n less than or equal to 0 will be represented in the form of. So it will be in the form of like this. So x of n is equal to 3, 5, 2, 1, 4, 7, and here the arrow mark is not indicated. So this will be the starting. The first term will be the starting corresponds to the n is equal to 0. So this is the fourth way how we are going to represent the signals. Then based on all this representation and the signal, how these discrete time signals are. That means what are the different types of elementary discrete time signals. If you see here, there are 7 different types of elementary signals which are the basic building blocks of the construction of the more complex signals. This we can see here. There are several elementary signals which plays a vital role. This plays a vital role in the digital signal processing as well as signals and systems. So what are they? The unit step sequence, unit ramp sequence, unit parabolic sequence, impulse sequence, sinusoidal sequence, real exponential sequence, and finally complex exponential sequence. So these are the main signals which plays a vital role in both the signals and system as well as all the signal processing system. Let me see step by step, one by one, what is these elementary signals plays. So first one, unit step sequence, how it is going to represent. If you see here, it exists only positive time. It exists only positive time, and is 0 for negative time. So okay, if it is exists, it is positive, and if it is not exist, then all that will be represent in the form of negative time. You can see it here. For example, u of n is equal to 1 for n is equal to greater than or is equal to 0. So how it is going to represent? You can see in the graphical representation. So for n greater than or is equal to 0, for n greater than 0, 1, it is greater than 0, greater than 0. So all greater than 0 value will be indicated with the value 1. That's why we are calling it as a unit step sequence. Okay. So if the condition n greater than or equal to 0, then all the values will be in a positive, that is 1, unity. So this is the graphical representation you can see here. So what it is saying, if a step function has a unity magnitude, then it is called unit step sequence. So what here we can see here, it is having a unit step magnitude. Okay, unity magnitude we have here. That's why this representation, what we are calling it as a unit step function. The second one, shifted. So what will be the shifted? That means here you can see, you can compare these two equations. It is u of n and it is u of n minus k. That is k times it is going to shift. For example, you can see here, you compare these two diagrams, it starts at 0, that is u of n is equal to 0, and if you see here, it is starting from u of n is equal to k. That means how many times it is going to shifting? It is going to shift k times. That means after all completion of that, the value will start from k is k. So that's why this these two representation you can see, one is unit step and what will be the shifted version of the unit step sequence. Now coming to the second one, which is unit ramp sequence. So what it says, a unit ramp sequence is that sequence which starts at n is equal to 0 and increase linearly with the time. You need to keep it in mind that it starts at n is equal to 0 and increases linearly with the time. So if you see here, the condition r of n, which is unit ramp sequence, is equal to n for n greater than or equal to 0. Okay. So if you see the diagram, it starts at n is equal to 0, n greater than or equal to 0 now. So it starts at n is equal to 0 and increases linearly with when. As n is going on increases, the value is also going to increases. So you can see that representation. See here, 1 for n is equal to 1, for n is equal to 2, for n is equal to 3, for n is equal to 4. As the n value is going on increasing, automatically the ramp sequence is also going on increasing. So this is nothing but the unit ramp sequence. So what will be the shifted version? You can see here, it is r of n, and r of n minus k means k times it is going to shift. So k times shifting means here it is started at the value 1. Now after shifting, he has taken one example. You can see here, r of n minus 2, that is r of n minus 2 means 2 times shifted, that is 1, 2, that is the value will start from 3 value. Two values will be shifted. Here it is started at 1, n minus 2 means 1 completed, 2 completed, so the values is started from 3. So 1, 2, 3. So this is the shifted version, how it is going to shifted in the unit ramp sequence. The third one, which is unit parabolic, and the condition is this one, p of n is equal to n squared by 2 for n greater than or equal to 0, and it represents like this. You can see here, this is the discrete parabolic, it will be in the form of parabolic. If you see here, it will be like this, parabolic conditions. And the shifted version, if you see here, the shifted version means n of minus k. If you see here, it is, for example, he has taken p of n minus 3, 3 times shifted, that means the value is started at 4, and it is the shifted version of the parabolic conditions. Okay, so this is unit parabolic sequence. The next one, unit impulse functions, very important, or unit sample sequence, and it is given in the form of del of n is equal to 1 when for n is equal to 0. That is, if n is equal to 0, the value will be 1, rest. If n is not equal to 0, then all values will be equal to 0. Now you can see that shifted version. That means if it is shifted to n minus k, what happens? The value will be 1 for n is equal to k only, and for n is not equal to k, the value will be equal to 0. It is the shifted version. If we can see that, if we see that n is equal to 0 means it is having the value 1. If n is not equal to 0, you can see there is no values. That means this is the condition. And if it is shifted version, just he has taken one example, del of n minus 3. So that is n is equal to 3. At n is equal to 3, the value will be equal to 1. Rest all the values will be equal to 0. So this is the another unit impulse response. Next one, sinusoidal sequence, and it is very important where in the upcoming subjects, whatever it may be, these conditions will be used repeatedly. So this is the main thing. The discrete time sinusoidal sequence is given by x of n is equal to, it is nothing but a signal where it consists of some information where a is an amplitude and the information is nothing but sine of omega n plus phi. So this is the sinusoidal sequence. See here, where a is the amplitude, is angular frequency, is phase angle. This is the angular frequency and this is the phase angle in radians, and n is an integer. So what is the value of this n? N is nothing but the integer value. So the combination of all these things is nothing but sinusoidal sequence. So it will represent this sequence, sinusoidal sequence. It consists of amplitude, it consists of phase, okay, it consists of phase, and it consists of some angular frequency, and finally what will be the value? The value will be integer, the value will be n. What will be the value? That will be either 1 or 0. So the odd combination is said to be a sinusoidal sequence. So n is equal to 2 pi by omega, where n and m are some integers. You can see here what I have drawn here, the representation, graphical representation, it will be in the form of sinusoidal. If you see here, it is in the form of sinusoidal. So x of n is equal to amplitude, sine of all the angular frequency and the phase angles, all the combination will form a sinusoidal sequence. Real exponential sequence, this is also one of the important signals, elementary discrete time signals, where for all the conditions, the condition x of n is equal to a to the power of n. So for this, when a greater than 1, you can see the representation exponentially increases at the negative side. If a is greater than 1, it is exponentially increasing at the negative side. If x of n is equal to a to the power of n, you can see it is exponentially increasing at the a greater than 1 side. If x of n is equal to n, that is a less than or equal to minus 1. So a is less than or equal to minus 1, it will be represented in the form of these ones. That is 0 less than or equal to, a less than or equal to 1, this one, a less than or equal to. If a is less than or equal to 1, all the left hand side it is exponentially increased. And for a greater than or equal to, you can see all the real values, that means positive values, it is increasing exponentially at the positive values. And if a is less than 1, this is the final representation of the real exponentially. That means it is increasing exponentially. Fine. And finally, the classification of discrete time signals. As I told you, the continuous time signals will be which is nothing but the analog signal, and discrete time signals. Okay. So when we are going to say that continuous time signals, every instant of time, the signal is defined for every instant of time, which is known as continuous time signals, and they are also called as analog signals, and it is denoted as x of t. All the analog signals or discrete continuous time signals will be represented with as x of t. They are continuous in amplitude as well as time. So they are continuous in amplitude and time. That's why we are calling it as a continuous time signals, and it is represented as x of t. Similarly, discrete time signals is nothing but the signals define only discrete time, and the second one is the discrete time signals are continuous amplitude but discrete in time. It will be continuous in amplitude, okay, it will be continuous in amplitude, but if you see here, it is discrete in time. That means not continuous, it is discrete, like segregation part. So that's one, and this discrete form, this discrete time signal is represented with the help of with the parameter x of n. So this is x of t, which is analog signal, and x of n is represented for the discrete time signals. And finally, by keeping these two in mind, that is both continuous and discrete time signals, the further classification of the signals are deterministic and random signals, periodic and non-periodic signals, energy and power signals, casual and non-casual signals, even and odd signals. So both we can see these 5 types of signals in both continuous time signals as well as discrete time signals. And finally, we will see what is deterministic and random signals. It says that A determinate signal is a type of signal that behaves in a completely predictable way. That means its value, magnitude and phase is always known. We know the values of magnitude and phase, and we can write this in mathematical representation also. Why? Because we can know all the magnitude and phase. By knowing all this, at any moment of the time, we can know the magnitude and phase. Because of that, we can describe these deterministic signals in the mathematical equation. And finally, in simple terms, there is no randomness or uncertainty in a determinate signals. It follows a fixed pattern. There will be no random pattern. And finally, this is one of the example. The sinusoidal sequence x of n is equal to cos n is one of the example. Good example for the deterministic. Exponential sequence is also one of the good example, and ramp signal is also one of the good example. So coming to the random, it is quietly opposite, where the main thing is the signal is obtained in uncertainty about its occurrence, where there will be no fixed path. It will be occur randomly. So if you see that, this is the main good graphical representation of deterministic signal, where it has a fixed value, fixed path. There is no uncertainty. If you see here are uncertainties and there is no fixed value. So this is a deterministic signal representation, and this is the random signal representation. So by this graph, we can easily come to know what is difference between deterministic as well as random signal. The next one is periodic and non-periodic signal. The name itself telling a signal which has a definite pattern and repeats itself at regular interval of times. These are the main important points we need to keep in mind when we are going to say that it is a periodic signal. Means a signal which has a definite pattern and it should regularly repeats in the regular intervals. Then that type of signals we can call it as a periodic signals. Then quite opposite of that, that is it does not repeat at regular intervals, then that type of signals we are going to call it as a non-periodic signals. So best examples, you can say x of n is equal to x of n plus capital N, and this is one which is periodic. It is in a fixed path and in a regular interval of time it is repeats itself at a regular interval. And if we see here, this is a non-periodic signal, there is no repetition, and see here, not repeats at a regular interval of time. There is no repetition. It is stopped from time between minus t to plus t. So we can call such kind of signals as non-periodic signals. And the next one, energy signals and power signals, very important. Why? Because this comes in each and every communication part. So energy signal will be classified. However, there are some signals which can either be classified as energy signal nor power signals. So this is the equation for the energy. Capital E is equal to summation n is equal to minus infinity to infinity mod x of n whole square. And the average power of the discrete time signal, the power is given as power is equal to limit n tends to infinity 1 by 2n plus 1 summation n is equal to minus n by plus n mod x of n square, where for digital signal x of n is equal to 0 for n less than or equal to 0. So these are the two representation of the continuous as well as the discrete. Both in both continuous and discrete time signals, the energy signals representation will be in this form, power and energy. So here, this is the main point we need to keep it in mind. A signal is said to be a energy. When we are going to call it as a signal and energy signal means if and only if its total energy capital E over the interval minus infinity to infinity is finite. That is minus infinity to infinity, the energy of the signal, total energy should be finite. You can see the condition 0 less than or equal to capital E less than or equal to infinity. In this condition, the signal, total energy of the signal should be in a finite. And what will be the average power? The power should be equal to 0. So energy signal, when we are calling, when energy signal in the limits minus infinity to infinity, the total energy should be in a finite form and power is equal to 0. Similarly, when we are going to call it as a power signal, the average power P is finite, but that means 0 less than or equal to P less than or equal to less than infinity. So for that, the power signal total energy E is equal to infinity. So then with these conditions we can say that the signal is said to be a power signal. And finally, the casual and non-casual, when we are going to call it as a casual signal, it is casual when x of n is equal to 0 for n less than 0. Otherwise the signal is non-causal signal. So a discrete time signal x of n is said to be anti-causal when if x of n is equal to 0 for n greater than 0. So with these two conditions, we can say which signal is a causal and which signal is a non-causal signal. And finally, this is the thing. This is also one of the main important signals in the discrete, both discrete and continuous, that is nothing but the even and odd signals. So the combination of signal will be expressed as a sum of even and odd components, x e of n, which is an even component, and x naught of n is said to be a odd component. That is, the combination of the sum of two signals, that is even signals and odd signals, will be formed as a signal representation x of n. So we can call even signal as a symmetric signal and odd signal as an anti-symmetric signal. So you can see the differences between both the even signal as well as odd signal. So even signal we can call it as a symmetric, and odd signal we can call it as a anti-symmetric signals. So first thing you can see here, a discrete time signal x of n is said to be a symmetric signal if it satisfies the condition this one. It should satisfy, that is, x of n is equal to x of minus n. For all the values of n, the signal x of n should be equal to x of minus n for all the values of n. But quite opposite here, if you see here, what will be the anti-symmetric? That is, for x of minus n is equal to, it will be minus x of n, which we can say it as a anti-symmetric signals. Fine. You can see here x of n is equal to x of minus 1 minus n, which is even signal, and minus x of n is equal to x of minus x of n. Sorry, here which will be equal to odd signal. You can see the two differences. And the next one, even signals are symmetrical about the vertical axis or time origin, hence they are also called symmetrical signal. Cosine sequence is one of the main example of the even signal. That means whatever the equation representing with the term cosine, then that signal will be said as a even signal. So opposite to this, odd signals are anti-symmetrical about the vertical axis, hence they are called anti-symmetrical signal. Sinusoidal signal, that is the equation which is represented with the term sine, will be called it as a anti-symmetrical representation. The graphical representation you can see here. See here, if this is the symmetrical form, if we fold this, that is x of n is equal to x of minus n, this total, if we fold this x of n is equal to x of minus n, the values will be same. Okay, I think it is clear. So the all x of n values will be equal to x of minus n. This value, if I fold within the origin, these all x of n values will be equal to x of minus n values. So these kind of graphs we can say it as a symmetrical graph. And here also you can see x of minus n values. See here, x of minus n values, if I fold this thing, all the x of minus n values will be equal to minus x of n values. So whatever the values here, x of minus x of n values will be equal to x of minus n values, which is said to be a anti-symmetrical form. That means if we fold this right hand side map to the left hand side, all the positive values become negative values and all the negative values will be equal to positive values. So these kind of signals we are calling it as a anti-symmetrical signals. So this is all the total data which is related to the signals, which is very important, where without knowing all the basics of the signals, we cannot go further to study about the digital signal process. So in the next class, we will discuss about the systems, what is meant by system. Thank you.